Trees are data structures of moderate complexity. They are very similar to linked lists in that nodes are stored at discrete locations in memory, unlike being stored contiguously like an array. For example, this node 2 can be at location 500, 5 could be at a very different location 1000, and 7 can be at say 3000, and so on. Like linked list, nodes in a tree also have pointers to each other. However, in a linked list, each node just had one pointer to the next element. That is, each node just pointed to one other element. While in a tree, each node can point to two or more elements. However, for simplicity, we will just consider binary trees where every node has at most two pointers. So, like 2 has two pointers, that is, 2 has two child nodes, 7 and 5. This 2 here does not have any pointers to any other nodes, while the 9 here has just one pointer to this node. Some basic terminology about trees. A node that does not have pointers to any other node is called a leaf node. The node here 6 points to 5 and 11. So these two nodes are child nodes, while 6 is the parent node. And a node that does not have a parent node is called the root node. Okay. So trees can be balanced or non-balanced. Intuitively, just looking at the figure, you can see that the tree to the left is very unbalanced, skewed to the right, while the tree on the right hand side looks more balanced. More formally, if the difference between the shortest and the longest branch of any node is more than 1, the tree is called non-balanced. For example, here, the left branch here, there is no left branch, so the height of the left subtree is 0, while the height of the right subtree is about 5. So, since there is such a big difference between the left subtree and the right subtree, this tree is called non-balanced. On the other hand, if you look at this tree here, the left subtree is of height 2 while the right subtree is of height 2. So it's certainly balanced at node 4. Here again, the right subtree is of height 1 and there's no left subtree. So the left subtree is of height 0, but the difference is just 1. So it's still balanced. However, if say there were another node here, now the right subtree is of height 2 while there's no left subtree which is of height 0. So now the difference between the left subtree and the right subtree for a particular node is greater than 1. In that case, this tree would be called an unbalanced tree. But as it stands now, it's a balanced tree. So a couple of interesting properties about balanced trees in general before we look at binary search trees. So the tree here is a balanced tree just because the height of the left subtree and the right subtree is same for all the nodes. In a balanced tree, as you can see, the root has just one node, the next level has two nodes, and the next level has four nodes, and so on. So if there are n nodes, we roughly have n by 2 nodes at the leaf. Also, because we have one node here, two nodes at the next level, and four nodes at the next level, the height of a balanced tree is typically log n, that is log n base 2. While on the other hand, an unbalanced tree can have a height of even n. So this is an unbalanced tree. So if there are n nodes, the height of this tree is the height of this tree is 1, 2, 3, 4. So an unbalanced tree can have a height of n, while a balanced tree has a height of log n base 2. So now let us look at binary search trees in specific. A binary search tree can be balanced or unbalanced. However, all binary search trees have one important property, that is, the value to the left child, the value in the left child is always less than the root, while the value of the right child is always greater than the root. So as you can see, this property applies for every node in the tree. Going down again, here 10 is the parent node. The value to the left is 8, which is smaller than 10, while the value to the right is greater than 10, which is 12. Or all the numbers in this subtree are less than 15, while all the numbers in this subtree are greater than 15, and so on. So if we have to look up a number, let us say we are searching for a number 25. We just want to check if 25 exists in a tree. We start from the root. Specifically, we want to check if 25 exists in a binary search tree, not just a tree, but a binary search tree. So we start from the root, and the number we are looking for is 25, which we know is bigger than 15. So we know that 25 is to the right of 15. So we can just skip all these nodes, the entire left portion of 15, and just go here. Again, we know 25 is bigger than 20, so we can just skip this left portion and just go right. There you go. So we eventually found 25. What is interesting is the complexity of searching for a number in a binary search tree. So in this case, we just examined one node at each level. So we examined at this node here, we examined this node here, and we examined this node here. So we just looked at one node at each level. So we know that in a balanced tree, the height of the tree or the number of levels is big of log n. So in a balanced tree, the amount of time it takes to search a node will also be big of log n. On the other hand, in an unbalanced tree, there can be up to n levels. The height of a tree can be up to n. So to search a node in an unbalanced binary search tree, our complexity is big O of n. So that was a quick overview of binary search trees. Now let us take a very quick look at self-balancing trees. So sometimes when you keep on inserting values, a tree can become unbalanced. But we always want our tree to be balanced because we know that in a balanced tree, the complexity of inserting or searching for a node is log n, while in an unbalanced tree, it is big O of n. For example, say I'm creating a new binary search tree with 10. I then insert 20. The tree is still balanced. And now I insert 30. Oops, now the tree has become unbalanced. So as to prevent a tree from becoming unbalanced, there are some algorithms that would make sure that the tree always remains balanced. So let's take a quick example at a self-balancing tree. One such a tree is called AVL tree, named after its founders. So this tree at this point is balanced because the left subtree is 0 while the right subtree is 1. The difference in the height is not greater than or equal to 2. So now let us say I would like to insert a new node. Now the tree is unbalanced because for this node 3 here, the left subtree is 2 while the right subtree is 2 while the left subtree is of height 0. So this tree is now unbalanced. However, what this AVL tree does is that in constant time, that is as soon as you add phi with no additional cost in terms of time complexity, the tree will adjust its pointers in such a way that the tree will become balanced again, like this. So previously the tree was like this, unbalanced at 3, but in constant time complexity the tree adjusts itself. So now the tree is balanced. This height is 2 and this height is 1, so it's still balanced. The good news is, for programming interviews, you typically don't need to worry about the details of self-balancing trees. You can typically just assume you are using a self-balancing binary tree like an AVL tree or a red-black tree or whatever. So just to summarize, we are talking about complexity in binary search trees. Binary search trees are binary trees where they have the special property that the left child or the left subtree is always less than root, while the right child or right subtree is always greater than the root. When you like to insert a node in a balanced tree, you just got to look at the point at which you want to insert a node. Like if I say I want to insert 30, you just look for the right space to insert 30, just stopping once for each level, and there are log n levels in a balanced tree, so the complexity is log n. Likewise for search, if you want to look up 25 or 16, you just go like this, or you just look at one node at each level, so it's log n. And similarly, delete is log n too. Deleting a node from a tree is not that common in programming interviews, so we can gloss over those details. While in an unbalanced tree, insertion is big O of n because unlike a balanced tree where there are just log n levels, an unbalanced tree can have as many as n levels. So if you want to insert a node, if you want to insert the node which is larger than all the existing nodes, you start here, you go right, you go right, you go right, and you insert here. So insertion in an unbalanced tree can be O of n. And similarly, search can also be O of n, because if you want to look up this node here, right, you start from the root and you go all the way down looking for that node, and you look at n nodes on the way. So search in an unbalanced tree is O of n. So now let's take a pause to tackle this warm-up question related to binary search trees.